Now we are doing part C, which is saying that we have the aqueous concentration of carbon dioxide, right, in an unopened can of soda, blah, 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 blah. The Henry's law. So Henry's law, calculate the partial pressure. We are using Henry's law. We know what Henry's law says. It says S is equal to KH times P, okay, where S is the solubility, and then K is the Henry's constant, and then P is the pressure, right? So we have it like this. Now, let me tell you, we have two versions of Henry's law. This is the first one. The other one is the one we use when we get two temperatures, okay? If we are to get two temperatures, right? Here, what did we get? One temperature? Okay, here we got one temperature. So it's going to be, let's see what we had here. So everything is going to be at the same stuff. So because of that, we use the one value, okay? We use the one value. But if we were to compare at two different values, then we are going to need, or two different pressures. If we were to compare the solubility at two different pressures, then we are going to have to use this one. This is the first one. Then the other one says that we can just say S1 over S2 is equal to P1 over P2. That's going to be the other one, okay? S1 over S2 is equal to P1 over P2. Don't ever forget that one, right? If you know that one, then we can say that, oh, you now know something about this Henry constant. So you should know S is equal to KHP, and then this one. S1 over S2 is equal to P1 over P2. We can also say S2 over S1 is equal to P2 over P1. Basically, now let's go for it. Calculate the partial pressure. Okay, so that means I must have solubility and I must have the pressure at the same temperature. So here, 0.17, the aqueous concentration, that's the solubility. So I can say S is equal to KH times P. And here they want the pressure, so I'll say S over KH is equal to P. What's my solubility? 0.017 molar divided by, what is my K? The Henry's law constant at the same temperature here is 3.4 times 10 to the negative. So it'll be 3.4 times 10 to the negative 2 molar per atmosphere. This will give me my pressure. So let's go ahead and let's calculate it. All right, and here the solution was going to be 0.5 atmospheres. That's going to be the pressure, 0.5 atmosphere, and we are done. So that's going to be the pressure, and we are done. Let's go to number D. Let's see if, okay, there's still time. So let's go to D. Hydrogen peroxide decomposes in the presence of HBr according to the following mechanism. All right, blah, blah, blah. Write down the molecularities. Molecularities. Let's go. Step one is we do the molecularity of step one. How many total? Remember, molecularity means the total number of molecules in the reactants. So here we have one here and we have one here. When we add them, it's going to be 2, and we write it as bimolecular. Okay. There's 1 is unimolecular, 2 is bimolecular, total of 3 that they can't pass 3. The total of 3 would be termolecular. So that's going to be, now let's go for step 2. What is it going to be? 1 here, 1 here. This is going to be again bimolecular. That's going to be bimolecular. Right. Now let's go to part 2. It's saying identify the intermediate. Remember, it's something that is made and then used up in the same reaction. I can see is this guy. He is made here and then he is used up here. So our intermediate is going to be OBr minus the aqueous. That's going to be the intermediate. Then part 3 says, what is the overall reaction? Overall reaction? All right, let's go ahead. Let's put the two guys, H2O. If we want, we can cancel it from here, really. So what we are going to do is we are going to add, okay, let's just do it. Let's have it H2O2 aqueous plus Br minus aqueous giving H2O aqueous plus OBr minus aqueous, right? And then here we have again the step 2, which is going to be H2O2 aqueous plus OBr minus aqueous giving H2O aqueous, okay, aqueous, let's put aqueous, AQ, aqueous, plus we have Br minus aqueous, and then plus O2 gas. Okay, now basically what we do, we combine these two. So let's see if we can add H2O2. There's another H2O2, so we have 2H2O2 aqueous. We combine everything on the left, okay? Plus we have Br minus aqueous, and then we have OBr minus aqueous, and then this is giving us, what do we have on the right? We have H2O and another H2O, so we have 2H2O aqueous plus OBr. Please, OBr is not the same as Br. OBr minus aqueous, and then plus Br minus aqueous, and then plus O2 gas. Okay, now we look for anything that is there, that is appearing on both sides. Br minus and Br minus. OBr minus and OBr minus. There you go. So what do I have? 2H2, my remain, that is 2H2O2. Please, H2O2 is not the same as H2O. This gives me 2H2O aqueous plus what else? O2 plus O2 gas. And this is my overall reaction, and I am done. Now let's go to part 4. Part 4 is saying, given that the rate law is this, which step is the rate determining step? Step 1. Step 1. The slow step is the rate determining step. Okay, the slow step. Now let's go to E. The rate constant is blah, blah, blah. Calculate the value of EA. So the moment I see myself having two temperatures and they're talking about EA and rate constant, I'm going to use the Arrhenius that says ln K2 over K1 is equal to EA over R multiplying 1 minus T1, 1 over T1 minus 1 over T2, 1 over T2. And here they want the value of EA. So basically, we'll go, let's first get this. Let's first put the things and then you see. So it's going to be ln. What's my K2? Remember, I'm going to go here and the rate constant at this is here. So I can call this K1 and this is T1. And here is T2, which makes this K2. So now what is T2? 50 degrees. Remember to change it to kelvins. Remember you say 0 kelvins, absolute 0, is equal to negative 273 degrees Celsius. So to go from degrees to kelvins, from negative 273 to 0, I add 273. And to go from kelvins to degrees, I subtract negative 273. So I want to go from degrees to kelvins, I add 273. So you say 50 plus 273. So let's put it, I would say 50 plus 273. What would I get? 323. So anyway, ln, what is my K2? K2 is 0.075 per second over, what's my K1? 0.032 per second. This is going to be equal to EA over, what's my R? Remember the R, you get it on the last page, which is going to be page 10. Here's my R8. You take the 8.3141. Okay, so it's going to be over 8.314. And then you have joules per Kelvin per mole. This is multiplying 1 over, let's go back to our guys. We have 1 over, what is it? T2 is 70. So 1 over, we say T1 first. We found it to be 323 kelvins. Okay. 1 over 323, let's say first 1 over 323 minus 1 over, what is the other one? 70 degrees. So I'm going to say it gives me 343, sorry. It's going to give me 343. Okay, that's going to be it. Let me put it just to confirm. Here, 70, yes, 343. And I can say my units are 1 over kelvins. Okay, now let's go. So I'm going to say here 0.075 divided by 0.032 is equal to, then I'll say ln of the answer. I would get 0.851. Okay, 0.851. So here I got 0.851. 7. So I would say add 852. 0.852 is equal to, let me say 8517, just to keep it big. Oh, 7.5. So 85118. Okay. Then what happens is this. I'll take this guy, this EA. You see, this thing is multiplying. Let's have it. 1 over 323 minus 1 over 343. So I'm going to say here, fraction 1 over 323. Then I'll say minus fraction 1 over 343. Okay, I get here. Oh, I get a very, very small number. Okay, I get a very, very small number. And I'm going to say that it's going to be, let me take it to the other side. I'm going to, you see this value here, it is multiplying. When it comes here, it will divide. So I can say this is divided by this fraction, 1 over 323 minus 1 over 343. Okay. And it is equal to EA over 8.31. And I'll take 8.31. So I would say here it is equal to, so I'm going to say 0.8518 divided by that answer. I would get 4,718. Okay, I'll get 4,718. Then I'll say that 4.718. Okay, or we say 4.72 times. I got 4.72 times 10 to the power of 3. Then I'll say multiplied by 8.31. This is going to be my EA. Okay, so I would say 4.72 EXP3. This one I would say now times 8.31. I would get it as 39.2 times 10 to the power of 3, which I could say, that's my EA, which I could say 3.92 times 10 to the power of 4. Okay, and remember what it is now. Here I had per second go, and here I had 1 over Kelvin go to the other side, divide, it became Kelvin. So my activation energy is going to be joules here. Is it joules per mole? I'm not sure, but probably. Let me see. Let me just confirm for you. All right, so in Arrhenius equation, it will be joules per mole. So this is going to be the final solution for activation energy. And we are done. Is there another question? What was this? That was E. Okay, so we are done. So that's the last question and we're done. Okay, bye.